Based on the latest findings, such as observations from the Keck Telescope showing unusual emissions of nickel and cyanide around 3I Atlas, this interstellar object continues to astonish scientists. It appears that this object is pushing the boundaries of our understanding with its strange behaviors, such as jets facing the sun and abundant water emissions. Let us take a general look at these anomalies and then examine them step by step. Stay with me on Astraeon. Comets usually change their brightness when they approach the sun because their ices evaporate. This is called sublimation, meaning direct conversion from solid to gas without becoming liquid. But Atlas? This one has stable brightness, without any sudden explosions or outbursts. Recent observations from the TESS telescope show that the coma, that is, the gaseous halo around the nucleus, is very faint, or even sometimes appears inactive. Why? Ordinary evaporation models say that brightness should increase as it approaches the sun, but here it seems to be resisting. Look at these Hubble photos from July 2025. It has a forward-facing jet that is 10 times longer than its width, and it points directly toward the sun. This coma is not normal at all. It seems like it is throwing sunlight forward, not backward. This behavior does not match the thermodynamic models, that is, the laws of heat and energy, that we have for comets. Why is it so stable? Perhaps its materials are such that they absorb heat differently, because TESS observations show the coma is very faint and the dust ejection rate is low, which is slower than ordinary comets. Or perhaps this stability is due to water emissions from icy fragments around it, not directly from the nucleus surface, which makes its activity slower and without outbursts. Perhaps its strange chemical composition, like high nickel without iron, is a sign of industrial-like processes in its external origin that increase thermal resistance. But the chemical compositions of Atlas are truly one of the most complex parts. The chemical ratios in the gases around it are unusual. For example, the ratio of CO, that is carbon monoxide, a gas released from ices in comets, to H2O, that is water, is very high. Water is low, but CO2, that is carbon dioxide, is high. James Webb observations from August 2025 show that this object is full of CO2 and nickel. Now, what is nickel? A metal used in industrial alloys. But here, nickel is more than iron, whereas in ordinary comets, iron is more, and the nickel production rate relative to CN, that is cyanide, a toxic chemical compound but common in the cosmos, is very high, even higher than the average for comets in our own solar system. If this mass is truly interstellar, why is its composition so similar to something we make on Earth, but with key differences? These data challenge our chemical models, because we expect to see simpler compounds like water and methane, not these complex alloys. Let us also talk about possible structural changes. The nucleus of 3I Atlas is large, diameter over 5 kilometers, mass at least 33 billion tons. Could the nucleus be binary, meaning two pieces orbiting each other? Or perhaps partial disintegration, meaning part of it separates? Or unstable rotation that causes its shape to change? But so far, observations have not shown outbursts or fragmentation, meaning nucleus breakup like other comets. The dust ejection rate is low, and its activity is stable. This does not match dynamic models, that is, laws of motion and force, because we expect the nucleus to become unstable with solar heat. See, this is exactly where the data complicates everything. Why is it so large and stable? Could it be part of an old system that no longer exists, and this size is a sign of its very high age? Regarding the tail and interaction with solar wind, I must say that the tail of this object is strange. It has an anti-solar tail, meaning a tail that points toward the sun, not away from it. Usually, comet tails are pushed backward by the solar wind, that is, the flow of charged particles from the sun. But here, the tail extends in both solar and anti-solar directions. And it is predicted that spacecraft like Europa Clipper and Hera will immerse in its ion tail in October and November 2025. This means they can measure the magnetic draping structure, that is, anoither the wrapping of the magnetic field around the object. Interaction with a solar magnetic field may cause changes in the tail's shape and direction. But why the anti-tail? This is not consistent with usual solar wind models. It seems like its materials interact with the wind in a way that reverses the direction. The interesting point is that even new models do not provide answers. Why are these behaviors not a sign of some instability in interstellar materials? Let us talk a bit about new scientific findings. In October 2025, new data from the debrief shows that the low dust ejection rate challenges behavioral models. Comparing data shows that nickel production relative to cyanide is much higher than average. These analyses freely suggest that perhaps Atlas came from a system with different chemistry. These anomalies not only challenge dynamic and thermodynamic models. For example, why is its non-gravitational acceleration, that is, a force other than gravity that changes the path, not matching the models? If this mass is interstellar, why is its composition so similar to our comets, but with key differences? Could it be a sign that cosmic materials are similar across the galaxy, but with local variations? Or perhaps 3I Atlas is part of a destroyed system, and these behaviors are remnants of that. Is this a sign of unknown processes in interstellar space, like interactions with giant molecular clouds? New evidence shows that Atlas is releasing water like a fire hose on full pressure. This abundant OH, hydroxyl, emission, reported by researchers in Wired and Live Science, indicates a lot of water in its compositions and changes our understanding of other stellar systems. Also, its close pass by Mars on October 3rd UTC has been examined by spacecraft like ExoMars and Mars Express, providing fresh data on the tail structure and interaction with solar wind, which may indicate new instabilities. And recent images from the Keck Telescope show unusual emissions of nickel and cyanide around it, without much iron, which confirms this strange chemical composition. These data, as it approaches the closest point to the Sun on October 30th, may reveal more secrets and rewrite our cosmic models. Are these behaviors a sign of new physics, or just a cosmic exception? And if it is truly stable, why does it not change near the Sun? These questions remain open, and future observations until the end of October can answer our questions.